All right, 15.5, we're going to talk about 1,2 and 1,4 addition of conjugated dienes. So we're going to start looking at different reactions with dienes. They do some very interesting type of chemistry. All right, you're going to do electrophilic addition to the double bond. All right, and that's going to produce the most stable intermediate. Remember, it's all about stability. All right, for conjugated dienes, the intermediate is a resonance stabilized allyl cation. We know this stuff, guys. I'm just reviewing this, and this chart's all words. I hate just words. I like structures. So let me just get through the slide, and then I'll start. Don't worry, the next slides I will explain all this. Nucleophile adds to either carbon 2 or carbon 4, both of which have the delocalized positive charge. Okay, it depends on the conditions. So let me show you what the last slide just said, but on structures. Okay, so we have a double bond, a single bond, double bond. So we have a conjugated system right here, conjugated. Okay, now if I add HBr, okay, one equivalent, all right, always assume it's one equivalent, even though it doesn't say it, but just assume it's one equivalent. It's going to add to it a pi bond. Now we learned this reaction last semester. If you have a double bond, you get a hydrogen on the least substituted and a bromine on the most substituted. Let me do it over here. So the hydrogen is going to go on this carbon, and the bromine is going to go on that carbon to give you that product right there. All right, based on Markovnikov's rule. Again, this is a reaction. Let me just kind of review that reaction. If you have a double bond, let's put an R group right here, plus HX. This is like one of the first reactions we learned last semester. You get R and you get X on the more substituted. And the mechanism, remember, the pi bond grabs the hydrogen, breaks the pi bond, and then it gives you a positive charge on the secondary. So your intermediate, let's write it over here. Again, this is just review. Your intermediate is either a plus charge here or a plus charge here if the hydrogen went here, but that's a primary carbocation versus a secondary. Secondaries are more stable, so this is the intermediate. That was Markovnikov's rule or Mark's rule. Okay, remember that? I'm just reviewing last semester. That's basically what this compound is. Okay, hydrogen adds to the least substituted, bromine adds to the most substituted. Okay, now it could add on this pi bond too, hydrogen here and bromine here, which would give you the same product. You just take that compound and flip it over. Okay, that's what's called the 1,2 addition, because if you label these carbons, this is 1, 2, 3, 4. H is going here, bromine is going there, so it's adding 1, 2. Okay, now let's look at the next product that forms. This is pretty interesting. Notice now you have a hydrogen adding on carbon 1, same carbon, but now your bromine, notice, is adding to carbon 4, and what's happening to your pi bond? Your pi bond now is shifting in the middle. Okay, so here I don't have any shifts. H here, Br here, everything else stays the same. Over here, H here, bromine here, but now I do not have these pi bonds anymore, but I have a pi bond in the middle. That's what's called the 1,4 addition. Okay, that's the 1,4 because it's adding 1 and 4. Okay, so addition of HBr to butyl-1,3-diene produces 3-bromo-1-butene, which is the 1 addition, or 1-bromo-butyene. Okay. So this we understand. This was last semester, pretty straightforward. But what is going on here? That's where this resonance stabilization is coming from that last slide. Okay, so let's look at the mechanisms. All right, and once you understand the mechanism, it's pretty straightforward. All right, so the first thing is your pi bond grabs the hydrogen, kicks out the bromine, gives you a plus charge. Again, last semester stuff. Okay, now what can happen is, notice I have a resonance structure. This pi bond can actually go into here, all right, form the pi bond in here and give you a plus charge here. This is a resonance structure. You have two resonance structures, okay, where either your plus charge is on carbon 2, so let's label these 1, 2, 3, 4, or your plus charge is on carbon 4. Plus charge on carbon 2, plus charge on carbon 4. Okay, this is going back and forth, back and forth, back and forth, back and forth. Well, what happens now is your bromine, okay, let's go back down here. Your bromine now sees both carbocations and says, all right, I don't care where your carbocation is, I'm just going to attack whatever positive charge I see. Well, if it attacks the carbon, this structure, where your carbocation is on carbon 2, that's the product that you're going to get. All right, so this leads to that product. All right. However, if you did the resonance and you have the plus charge now on carbon 4, okay, your bromine now is going to attack the 4 carbon to give you that compound. And that's the 1,4 addition. So it really depends. Is your bromine attacking the non-resonated carbocation, or is it attacking the resonated carbocation? All right, you technically have two choices. So are you going to get a mixture of compounds? What happens? Well, there are ways to control which product you can get. You can favor one reaction over the other depending on something we're going to learn is on how much energy is in the system, okay, and based on sterics. It's what's called a kinetic versus thermodynamic control, and we're going to see this theme over and over again throughout the semester, all right? Kinetic control reactions, all right, are usually done while it's cold. All right, lower temperatures. All right, while thermodynamic control, all right, are usually done in warmer temperatures. You usually have to heat these up, warm. Okay. So what the kinetic product, it's what's called a kinetic product. You're getting, so in this case, notice negative 80 degrees. All right, that's under kinetic control because it's cold compared to 40 degrees. I'm heating it up. Okay, so usually under the kinetic or the cold product, you get the fastest made compound. It's based on sterics, number one. Okay, and it's the one that is the easiest and the fastest. Let's say fast. Okay, so let's see how that applies here. Okay, so in this case, the kinetic product is your 1,2 product. That's your kinetic. I'll put it down here. It's your 1,2 product, where your thermodynamic is going to be your 1,4 product. Okay, so it's based on sterics, and it's based on what quickly happens. All right, so once your pi bond breaks, right, you get a plus charge on this carbon. Well, you don't really have enough energy for it to resonate. It's basically your bromine now quickly just adds in there and forms your 1,2 product. All right, you don't really have enough energy or enough time to actually resonate your compound. So because of that, it just quickly goes to your 1,2 product. It's the one that quickly makes it. Okay, the thermodynamic, after I explain the thermodynamic, it'll make more sense. The thermodynamic is based on the stability of your product. Stability of product. Something else I forgot to say on the kinetic. This is based on the stability of the intermediate. I forgot to say that, and that's really important. All right, sorry for this writing. This pen doesn't. I mean, my writing is horrible to begin with. Now it's even worse. Let me kind of redo that. I used a D instead of a B, anyways. I gotta write just lower. Stability of intermediate. Okay, so let's see why. This intermediate will have a plus charge over here. That's a secondary carbocation. This intermediate will give me a plus charge here. That's a primary. Which intermediate is more stable? The secondary. So it leads to that product. Okay? In the thermodynamic control, where you heat it up, it's based on the stability of the product. This is stability of the intermediate. This is stability of the product. So looking at these two compounds, which one is more stable? A double bond at the end of a chain or a more substituted double bond? I'm kind of leading you into the answer. Well, in this case, it's going to be the more substituted double bond is a more stable product. That's Zaitsev's rule. Okay? So here, the product is more stable. Okay, so a more stable product is based on thermodynamic control. A more stable intermediate is kinetic control. All right, so if you have two possible products that can form, you look at the intermediate. Whichever one is more stable, that's going to be the kinetic product. And it's usually done under colder environments because it's more stable. It's a lower activation energy. The thermodynamic one, it doesn't really care about the intermediate because you're warming it up. You're putting in tons of energy. It can make it over a barrier, whatever your activation barrier it is, because you're putting in more energy, it can make it over there. So it's not based on your intermediates anymore. It's based on the stability of your product. Whichever product is lower in energy, that's the one that's going to form. Okay, so let me just kind of review this because I know I got a little sidetracked there. Kinetic control is based on intermediate, stability of intermediate. The thermodynamic is based on your stability of your product. Okay, there is a nice graph right here to kind of show you this. Okay, nice. Yeah, it's a little confusing, but we'll work through it. Okay, here's my intermediate. My intermediate's the same. It doesn't matter which one. Okay, here is the one that's formed faster. This must be the kinetic product. Okay, my intermediate's the same. Lower energy, okay, because I don't have to make it over a large activation energy. All right, you know, in order to get the primary carbocations are much higher in energy. It's going to take much more energy to get to that primary carbocation, start adding to it. So notice that's a little bit higher than this transition state. So when I heat it up, I can make it to that primary, and notice my product energy is much lower in energy than the product of the 1,2. Okay, so it's an interesting thing that's going on. Higher energy, but more stable intermediate. Product. All right, less stable intermediate, more stable product. Less stable intermediate, more stable product. So thermo-controlled, okay, less stable intermediate, more stable product. The kinetic control is the exact opposite. All right, the kinetic control is more stable intermediate, less stable product. It doesn't care about your product. It just cares about the intermediate. Where the thermodynamic cares about your product, it doesn't care about the intermediate. Okay? So here's just kind of a review of it. All right, the transition state for the 1,2 has a lower activation energy, more stable. Okay, because it forms the more stable carbocation, more stable intermediate. The 1,2 addition goes fastest. The nucleophilic attack of the bromide on the C2 allylic carbocation is reversible at this low temperature. We didn't really talk about that, and it's not that important. The product forms faster. It's usually the quicker reaction, and it stops. Because the kinetics of the reaction determines the product, the reaction is said to be under kinetic control. It's based on the rate. That's why it's kinetics. Thermodynamic, the 1,2 addition is still the faster addition, but at 40 degrees Celsius, the bromide attack is reversible. So you can actually form the 1,2 product, but then it breaks apart, and then eventually it goes to the more stable compound. Again, we didn't talk too much about that. I just want you to understand what the difference between kinetic and thermo is. All right, the 1,2 product ionizes back to allylic carbocation. The 40 degrees equilibrium favors the more stable product. We talked about that. It's a more substituted double bond. That's why it's more stable. And since this is all based on the heat and the energy, that's why it's thermodynamically controlled. All right, we're going to stop here, and we will pick this up on the next video.